Okay, so part two, we're going to talk about geometric series. And a geometric series, again, is a sum from n equals 0 to infinity of ar to the n, all right? And what I started saying at the end of the last video is that one of the hallmarks of a geometric series is that you only see n in the exponent, and that's how you know you're dealing with a geometric series. You're going to realize that geometric series are one of your favorite types of series. It converges if absolute value of r is less than 1, meaning r is between -1 and 1. It's divergent otherwise. If it converges, so if absolute value of r is less than 1, the sum is a over 1 minus r, okay? So the series that I have here for you guys are all geometric. And you guys can see that in each of these, the n is only in the exponent, the n is only in the exponent, the n is only in the exponent. This we'll talk about in a second. Even the next one, x to the n is only in the exponent, which means you're dealing with a geometric series, okay? The ratio, sometimes you're going to want to write out terms of a series to figure out what the ratio is, what that r is, but a is always easy to find. You find a by plugging in your initial value for n and just seeing what the first term is. I would just actually pause the video, work through all these problems, and come back to me, or come back after each one, whatever you prefer. But try to work through them on your own. You should be okay. Like I said, if you need to, like for this first one, if you don't recognize what r is, write out some terms of the series and you'll see r very easily. It'll be the ratio between terms, what you have to multiply to get from one term to the next. So for the first one, the terms would be 1 plus 1/3 plus 1/9 plus 1 over 27 and so on, meaning r is 1/3. Okay, so first one, geometric series, absolute value of r is 1/3, which is less than 1. The first term, if you plug in n equals 0, you get 1. So when you do, the sum is a over 1 minus r, you get that the sum is 1 over 1 minus 1/3, or 1 over 2/3, or 3/2. Okay, moving on to the next one, pause if you need to. We have another geometric series. R is everything that's being brought to the exponent, so in this case, absolute value of r is 3/2, which is greater than 1, which is going to make this one divergent. Okay, if it's divergent, you can't find its sum, so you're done. All right, let me just go back. I didn't say convergent for the first one, and I got to write out divergent for this one, so hang on. Okay, so moving on to that third one, the sum of -3/5 to the n. Okay, again, it's a geometric series. Okay, absolute value of r would be absolute value of -3/5, which is 3/5, which is less than 1, so therefore I'm convergent. And then my sum is going to be a over 1 minus r. A is my first term. Okay, it doesn't say where I start from, so I start at n equals 1, which means that my first term is -3/5 to the first power. So when I do my sum, it's going to look like this. Okay, -3/5 over 1 minus -3/5, or -3/5 over 8/5, which is -3/8. So that is the sum of my convergent geometric series. All right, this last one, when you're given a list of terms, just figure out, is it geometric? Because you love your geometric series. You'll see in a couple weeks how much you love geometric series. I have, to get from my first term to my second term, 5 times what gives me -10/3. I would multiply by -2 over 3. And then again, if I multiply -10/3 by -2 over 3, I end up with my third term, 20 over 9. And if I multiply 20 over 9 by -2 over 3, I end up with -40 over 27. So this is a geometric series. Okay, r is the ratio between terms, and we just figured that out. That's -2/3. That's what I have to multiply to get from one term to the next. So, okay, so that makes my series convergent. And then I'm going to figure out my sum by doing a over 1 minus r. All right, a is actually right here. It's given to me. It's 5, and r is -2/3, so my sum will look like this. Okay, so I have my sum as 5 over 1 minus -2/3, or 5 over 5/3, which is 3. Okay, you guys will notice that I'm really going overboard with saying I have a geometric series on every one, whether it's convergent or divergent, what absolute value of r is, whether or not it's greater than 1 or less than 1. You need to be very showy when you're doing your series. You need to really say, hey, look at me. I know it's a geometric series. Hey, I know what r is. Hey, I know it's convergent, and so on. Okay, it's part of the fanfare of series. Okay, the next problem with geometric series I want to look at is a sum from n equals 0 to infinity of x to the n. Okay, this is a geometric series because n is only in my exponent. Okay, this one's a little different though. Go ahead and pause and list out the terms of the series starting with n equals 0 and come back to me. Okay, so seeing the terms of the series, I see to get from the first term to the next term, I multiply by x. To get from the second term to third term, I multiply by x, and so on, which means it is a geometric series. Okay, and that means that it will converge if the absolute value of r is less than 1.
So do you need this wheelchair? No? Okay, I'll get it tomorrow morning. Okay.
Yeah, but it's kind of a video. I'll bring you a special way.
Okay. How are you?
I'm good. No, no, what you were
Okay, and hopefully what you've noticed is that there's, okay, in class we're going to look at this step by step, but you can see if you start graphing a bunch of the terms of the series, and what I have in red, it mimics the graph of the function 1 over 1 minus x, the hyperbolic function 1 over 1 minus x, which is in black. The vertical that you see over here, oh, and I'm sorry, I missed it, is over here, here's my y-axis. This is my vertical asymptote over here. And you'll see if you continue to add on terms of that series, it's going to mimic it only for a certain amount of time, and it's consistent with the information that we already talked about. So we'll think about this, play around, and we'll talk about it more in class tomorrow. Okay, so not all series are geometric. I have on your outline a telescoping series, which is not covered on the AP exam, so we will not be covering it until after the AP exam. But I have the harmonic series. It's a pretty famous series, and for any of you music aficionados, the harmonic series actually, the terms of the series have something to do with harmonies and something I don't know. I honestly have no idea, but look it up if you're interested. That's why it's called the harmonic series. So in any case, list me out the terms of the series, and then we're going to talk about whether or not the series might converge or diverge. Okay, so I have 1 plus a half plus a third plus a quarter. If you go back to thinking about that geometric series with the piece of paper from the last video, from part 1, I'm starting with a sheet of paper and then adding on a half a sheet of paper, a third a sheet of paper, a quarter of a sheet of paper. I'm adding on pretty big pieces of paper in comparison to the half a sheet plus just a quarter of the sheet plus an eighth of the sheet plus a 16th of the sheet. The fourth term of that series was as small as the 17th term of this series. The fifth term of that series would be as small as the 32nd term of this series. So the terms of that series were getting a lot smaller, a lot faster. If I look at the partial sums on this, there's not going to be any pattern for them, and I won't be able to take the limit if there's no pattern. And what I can do is I can play around on the calculator, and I can sum and find some different partial sums of the series and realize that they are just going to continue to grow and grow. Okay, so one of the things that you can do on your graphing calculator, using the calc menu, you'll see that there's a sum feature, and I think it's on your shortcut sheet that you do the general term, comma, your variable, comma, your starting value, and comma, your ending value. So I came up with some partial sums. Okay, I did S sub 10, which is the sum of the first 10 terms, S sub 100, the sum of the first 100 terms, S sub 1,000, sum of the first 1,000 terms, and S sub 10,000, sum of the first 10,000 terms. I actually used alpha for some of this because your calculator's a little slow, but you can see that my partial sums are just getting bigger and bigger and bigger, and I want to take an infinite sum, okay, not just the sum of the first 10,000 terms. So if I'm going to add on infinitely many terms, the sum of the first 10,000 pales in comparison to what the value would be. It just appears to grow and grow and grow. Obviously, this is not concrete to say that the series is divergent. I will prove to you later on that the series is divergent, but right now we're going to assume that this series is divergent. I ask you to trust me. Okay, I want you to think about this. We have a theorem that if the sum of a series is convergent, if a series is convergent, then what does the nth term, the general term, have to approach as n gets out towards infinity? So I want you to think about it, really think about it. In order for the series to converge, what kind of value will I have to add on if I'm adding it on infinitely many times? I want you to really think about it, pause, and come back to me. Okay, and the answer is that I have to be adding on 0 every time. As n goes out towards infinity, I need to add on terms that are practically 0, because if I'm doing anything besides a plus practically 0, plus practically 0, plus practically 0, then there's no way for my series to converge. Okay, I want to know, is the converse true? So converse says, if the limit as n approaches infinity of the general term is 0, does the series have to converge? And I want you to think about that, and we'll discuss it in class tomorrow. Okay, this theorem can translate into a test for divergence of a series. So if a series is convergent, then the general term has to approach 0 as n gets big, as n goes out towards infinity. So the nth term test for divergence says that if that general term is not approaching 0 as n gets big, what do we know has to be true about that series? So again, pause, think about it, and come back to me, please. Okay, so if every convergent series has the general term approaching 0, if the general term is not approaching 0, then the series must be divergent, okay? And we call this the nth term test for divergence, okay? And it only works if the general term is not approaching 0. Let's look at some practices with that. Okay, so for these two series, I want to know, are they convergent or divergent? And if you look at them, the first question is, are they geometric series? And the answer, well, pause and think about it, and then come back. The answer is no, because I have n as a base in both the first example and the second example. All right, and right now, the only other option I have if I don't have a geometric series is to use that nth term test for divergence. Okay, so for that first problem, I'm going to take the limit as n approaches infinity of that general term there, and that would look like this. Okay, so I'm taking the limit as n approaches infinity of the general term, and you can either L'Hopital this or you can end behavior model it, either way. Pause, come back to me, but the limit should be 1/5. Now, according to that nth term test, what I'm looking for is a limit other than 0, and this is not 0. That's what's remarkable about this. Okay, and because this is not 0, the general term is not approaching 0 as n goes out towards infinity, we say that the series is divergent. Okay, let's look at the second one. Again, also, it's not geometric, so we're going to nth term test it. Here, again, pause, come back. But when I take the limit as n approaches infinity of that general term, okay, with the limit as n approaches infinity of n over 5 plus n squared, I do get 0 this time. Okay, right, you can either L'Hopital it or end behavior model, but you get 0 for your limit. And if you get 0 for a limit, the test fails. Okay, because just because my general term approaches 0 doesn't mean that I'm going to either converge or diverge. Okay, I can go either way with it. So the test fails, and for right now, we know nothing. Okay, or at least we know nothing about this particular series, and we would need a new test, which we don't have yet, but we'll have in a couple weeks. Okay. Okay, we just need more ways to test for convergence or divergence, and we'll come to those in a couple weeks. Real quickly, we have some properties. If I have two convergent series, if I multiply one of those series by a constant, okay, I can pull that constant out. And if I have a convergent series, then this series that's multiplied by a constant will also converge, because if I have a finite value to my sum, and I multiply that finite value by 5, or 2, or -1/2, or even 784, I'm still going to have a finite value to my sum. And then if I have two convergent series and I add them, I'm going to look at it as the sum of the general terms is the sum of the individual series, and if I have two convergent series, meaning they have a finite value to their sums, and I add or subtract those finite values, I will get another finite value, so this will also converge. Okay, I am out of time again, but that's going to be it for the video part of this, and we'll cover a couple more things in class tomorrow.